Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in previous sessions, we have discussed about solid mechanics and material subject. In this, we have learned various topics like simple stresses and strains, and then shear force and bending moment diagrams, and principal stresses and strains, and theories of failures. We have discussed in the previous sessions. So in this today's session, I want to discuss about bending stresses in beams. So here, bending stress and then tensile stress and shear stress and torsional stresses. These stresses are very important in solid mechanics and material subject. So that we should know about, so what do you mean by the bending stress? So what are the bending stresses occur in the beams? So how to calculate? So how it will be in bending stress, pure bending, the beams occurred, the shape. So all these things we will see in this topic. So that's why you should concentrate this bending stresses in beams. So before entering the subject, the topic, the student should know about this topic outcome. The student should be able to analyze the theory of simple bending for illustrating the distribution of bending stresses across the section beams under loading. So analyze. So after completion of this topic, the student should analyze the theory of simple bending and then illustrating the distribution for different for bending stresses. So in this topic we will see the simple bending theory and then the distribution of bending stresses across the various sections of beams under loading, under different loading we will analyze. So that after completion of this topic, the student be able to answer and analyze the theory of simple bending and the distribution of bending stresses. They can analyze and they can demonstrate. So what is the bending stresses in beams? So you have seen shear stress and bending moment, and then shear forces and bending moment diagrams we have drawn, and also we have seen simple stresses. But what is this bending stress in beams? We will see in today's session. So the bending moments and shear forcing are set up at all sections of a beam. You know, already we have seen when it is loaded with some external loads. So whenever the beam is loaded with external loads, suppose you take one beam, this is cantilever beam, so loaded with say at the free end the beam is loaded, clear? So at this condition there are some external loads, so how it will respond, the beam. So that is the concept of bending stress. So as a matter of fact, the bending moment at a section tends to bend or deflect the beam, and the internal stresses resist its bending. So how it will acting? So like this, the bending, or in the anti-clockwise, or clear. So all these things we will see in this topic. So the process of bending stops. The bending stops when every section, cross section set up full resistance to the bending moment. So the bending moments and shear forces are set up on sections of a beam, you know. So when it is loaded with some external load, how it will respond? Clear. The resistance offered by the internal stresses to the bending is called bending stress. So the resistance offered by the internal stresses to the bending is called bending stress, and the relevant theory is called as theory of simple bending. The theory related to bending, so that's why the theory is called as simple bending theory. So important points are, you note it, the bending stress is the combined effect of both tensile and compressive stress. So the bending stress will be occurred due to this tensile and compressive stress. See, in this diagram shown, the beam, the before deformation, the beam is like this. So after deformation, so whenever subjected to the external load, the bending beams, so the horizontal lines becomes curved, the vertical lines remain straight and rotate after deformation. So the horizontal lines and vertical lines. Vertical lines remain same, but horizontal lines are occupied. There is a curved shape. Clear? So here, the resistance offered by the internal stresses to the bending is called the bending stress. So whenever the external load is acting, it tends to bend or deflect the beam. Due to this internal stresses resist its bending. Clear? So the bending movement shown here diagram after deformation, the beam is bent like this. See, so the bending in a 2D diagram, there is a simply supported beam. Two ends are supported, simply supported. So whenever this beam is loaded with center load, the load is acting at its center, the bending occurs like this. So this is called as the bending, the related theory is called as the theory of bending. See, the bending in beams, any transverse section, you take, so this is neutral axis and neutral surface. So you can see in this surface, you can so mark it like this, A, B, C, D. So the bending in beams, see in clearly mentioned here, simply supported beam. Simply supported beam. And UDL load also acting here, and the point load. So this is point load and UDL. So after bending, the curve, the beam formed like this shape. So due to this point load, the movement is anti-clockwise, and then UDL also acting. So load is compression, and this will be in tension. It elongate, and this the bottom one is elongated and top portion is compressed. Top layer and bottom layer. So one more diagram shown here. So the cantilever beam, one end is fixed, another end is free, and this is overhanging beam. So some portion is overhanged here, not at its free. Overhanged. Overhanged beam. So the tension is, in this case, in upper portion, the lower one is compression. So the load is acting at its free, in this case. Suppose it is acting like this, so this is cantilever beam. Cantilever and overhanging. So the concept of pure bending or simple bending is, if a length of beam is subjected to a constant bending moment and no shear force, that is zero shear force, then the stresses will be set up in that length of the beam due to bending moment only, and that length of the beam is said to be in pure bending or simple bending. So the stresses set up in that length of the beam are known as the bending stresses. So if a length of beam is subjected to the constant bending moment, there is no shear force. So what will happen? The stresses will be set up in that length of the beam. Why? Because due to the bending moment only. So then the beam is said to be pure bending or simple bending. So the stresses set up in that length of the beam are called as bending stresses. So I will show you in this diagram. So only the bending moment is there. There is no shear force. So the bending moment diagram, already shear force diagrams and bending moment diagrams we have seen in shear force and bending moment diagram topics. So in this diagram, see in this beam, the load applied at C and D, and also the reaction forces are RA and RB. The shear force diagram drawn like this. The shear force is changes its sign positive to negative, and the bending moment is negative bending moment. So whenever the stresses set up in that length of beam are known as the bending stresses. That particular beam is called as pure bending or simple bending. Clear? So what are the assumptions in the theory of simple bending? So for deriving the theory of simple bending, have to assume we have to take some assumptions. So the material of the beam is perfectly homogeneous. So that is of the same kind and isotropic. That is of equal elastic properties in all directions. So the beam material is stressed within the elastic limit and thus obeys Hooke's law. You know Hooke's law, according to Hooke's law sigma, the stress is directly proportional to strain. So you can write the stress is equal to Young's modulus with multiply with strain. So the transverse sections which were plane before bending remains plane after bending also. So the material of the beam is perfectly homogeneous. So that is there is no other properties. There are equal elastic properties in all directions. In this case, the beam material obeys Hooke's law. The stress is directly proportional to strain within the elastic limit. The transverse sections which were plane before bending, they remains plane after bending also. These are the assumptions I have taken. The first one is isotropic material. The beam is perfectly homogeneous, and then material is follows Hooke's law, and the plane remains the same after bending also. And then each layer of the beam is free to expand or contract. So that is independently of the layer above or below it. And the value of E, the modulus of elasticity, is the same in tension and compression. And the beam is equilibrium. So there is no resultant pull or push in the beam section. Each layer of the beam is free to expand or contract. So the theory of simple bending, the before bending and after bending shown here beam. So this is bending moment applied. So that's why only bending moment is there. So this beam is called as said to be pure bending. And here the after bending, so R dash and B dash and S dash and D, the shape will be in the form of curvature. So that this is neutral axis, a layer. So top one is subjected to compression, and this one is tension. So consider a small length of a simply supported beam subjected to a bending moment. Simply supported beam subjected to a bending moment So as shown in figure. Here small elemental length taken dx. So now consider two sections AB and CD which are normal to the axis of the beam RS. AB and CD. Normal to the RS. So due to action of the bending moment, the beam has wall will bend as shown in figure. So in after bending, see, you can see here after bending the beam is shown here, the A dash B dash and the C dash D dash and the layer, the neutral layer R and R dash S dash. So since we are considering a small length of dx of the beam, therefore the curvature of the beam in this length is taken to be circular. There's only small portion we have taken, so that the curvature you can take as a circle. So a little consideration will show that all the layers of the beam which were originally of the same length and do not remain of the same length anymore. So this is a consideration while deriving this pure bending theory. The top layer of the beam has suffered compression, already I told you, and reduced it to A dash, C dash, the top layer. A dash, B dash, C dash, D dash. So this is RS. R dash and S. So top layer of the beam has suffered compression, this compression and tension, reduced to A dash, C dash. As we proceed towards the lower layers of the beam, we find that the layers have no doubt suffered compression, but to lesser degree until we come across the layer RS. Previously, the small elemental area is like this, RS. So which has suffered no change in its length, though bent into RS. So even though this layer bent, but there is no change the length. So if you further proceed towards the lower layers, you find the layers have suffered tension, as a result of which the layers are stretched. So the amount of extension increases as we proceed lower until we come across the lowermost layer, the BD. So lowermost layer is BD, which has been stretched to B dash D dash. So B dash D dash. So that layer stretched like this. So now we see that the layers above have been compressed and those below RS have been stretched. So the amount by which layer is compressed or stretched depends upon the position of the layer with reference to RS. So this layer RS, which is neither compressed nor stretched, is known as neutral plane or neutral layer. So neither compressed nor stretched is known as neutral plane or neutral layer. So already I told you, this layer is neutral layer or neutral axis. There is no change in its length. So this theory of bending is called as theory of simple bending. This type of phenomena is called a theory of simple bending. So the derivation part we will see. So derivation for bending stress, first you take a small elemental portion. Here A, B, C, D shown, and then this portion is PQ. And neutral layer is NL, or neutral axis is RS, and then take point O, and from O to here the curve, the neutral layer R dash S dash, take as radius, and then there is a top layer A dash E dash and B dash D dash stretch. One is in compression, another one is tension. So consider a small length dx of a beam subjected to bending moment as shown in figure. So as a result of this moment, let this small length of beam bend into an arc of a circle with O as center as shown in figure. So this let this small length of beam bend into an arc of circle. So arc of circle, this one. So this the bend like this. So the bending moment is acting at the beam is m, and theta is the angle of subtended at the center by the arc, and r is the radius of neutral layer. So now consider a layer PQ at a distance y from RS. So already shown in this diagram. Take distance y from its neutral axis. From its neutral axis y. Let this let this layer be compressed to P dash Q dash after bending. So you know that decrease in length of the layer. So what is the deformation occurred in the layer? Delta L is PQ minus P dash Q dash. Previously the layer is PQ before bending. See here. After that P dash and Q dash. So there is some change in their length. So that is delta L. Now you can calculate strain delta L by original length. So what is the change in length? PQ minus P dash Q dash by the original length is PQ. Clear? See here, take this the bending after bending diagram. So A dash C dash and P dash Q dash, that distance is here y. So now take triangle here P dash Q dash by these two, P dash Q dash by R dash S dash is equal to R minus Y by R. The R dash S dash is original radius, that is R, and then P dash Q dash is R minus Y. Y minus PQ is R, and P dash Q dash is Y. P dash Q dash is Y because that the distance is Y from its neutral axis. Now write this equation like this: 1 minus P dash Q dash by R dash S dash is equal to 1 minus R minus Y by R, and then so simplify. So we can write the strain is equal to Y by R. Y by R. So the Y is here the PQ at a distance Y from its RS. Clear? And then R is that radius of neutral axis. Clear? So now PQ is equal to R dash S dash, that is equal to neutral axis. So you can write the strain is equal to PQ minus P dash Q dash by PQ. So it is thus obvious that the strain of a layer is proportional to its distance from the neutral axis. So we also know that the bending stress is equal to elasticity into strain. So as per Hooke's law, it pure bending assumption already have taken. So it follows Hooke's law. So that the stress is directly proportional to strain. You can write in terms of elasticity is epsilon. So the bending stress, you can write elasticity into multiply with the strain, that is E into epsilon. This one already he derived in a previous equation, that is y by r. So now substitute the y by r in this equation, that is sigma b is equal to y by r elasticity, that is y into E by r. So this is taken as equation number 1. Similarly, write one more equation 2, second equation. Since E and R are constants in this expression, one is elasticity, modulus of elasticity, another one is radius. There is no change. Therefore, the stress at any point is directly proportional to y. So that is the distance of the point from the neutral axis. So the equation may be written as the first equation, sigma b by y is equal to E by r. The sigma b is equal to y into E by r. So you can write sigma b by y is equal to E by r. So the equation known as the bending stress equation, sigma b by y is equal to E by r. So one is the sigma b is bending stress, the units are Newton per mm square. E is Young's modulus, Newton per mm square. The y is distance of a section from neutral axis. So r is radius of curvature. These two are constants. There is no change. Since the bending stress is inversely proportional to the radius, so as per derivation, E sigma by y is equal to E by r, the bending stress is inversely proportional to the radius. Therefore, the maximum stress at the radius should be minimum and minimum stress at the radius should be maximum. This vice versa. Clear? So that the bending equation derived, sigma by y is equal to E by r. So the bending equation you can write sigma b E by r. So that is, so E by r, so bending equation, that is equal to m by I. So this is bending equation, bending stress equation. So what is this m? This is bending moment, and I, the moment of inertia. So you can take, so you can write this equation in terms of moment of inertia. M by I is equal to sigma by y is equal to E by r. You can take any two. E sigma y is equal to E by r, or E by r is equal to M by I. So here you know the bending moment, and then according to the section you can calculate moment of inertia. Clear? The moment acting at the beam, you know, and then you can calculate the bending, the moment of inertia. You know the bending moment of inertia for various sections. So substitute in this equation, you can find the bending stress. So that the E and R are constants in these expressions, and y is the distance of point from the neutral axis. So how to derive an equation like this? So that here in this session, we have discussed about the theory of simple bending. What is the concept behind this simple bending? When it is said to be pure bending, when it is said to be the simple theory of bending, what are the assumptions important in the theory of simple bending we have seen? The assumptions we have taken, and the first assumption is the beam is perfectly homogeneous, and then the material of the stressed within the elastic limit, that is Hooke's law, it should follow the Hooke's law, and transverse sections which were plane before bending remains plane after bending. So these are the assumptions we have taken. So based on these assumptions we have derived that equation, that sigma by y, that is sigma b by E by r. So this is the bending stress equation. So the value of E is the same in tension and compression. There is no change. The beam is in equilibrium. There is no resultant full or portion the beam section. So these are the assumptions I have taken for this theory of simple bending equation. Clear? So the before bending and after bending we have seen here, the diagrams shown, and then so according to the diagram I have taken, we have derived the equation. So see here, the important point is the RS layer is a neutral layer, and the above, the top layer is subjected to compression, and the lower layer is tension and compression. Clear? And then the amount of extension increases as we proceed lower until we come across the lowermost layer BD, which has been stretched to P dash D dash. And here see the layer RS, it is neither compressed or not stretched. So it is known as neutral plane or neutral layer. So this point is important. So there is no change in its layer length. So that's why this plane layer is called as neutral layer and the plane is neutral plane. The theory of bending is also called as the theory of simple bending. So these are the important points I have seen. So derivation in part take a small elemental length of the beam, that is dx, and take section PQ. So the PQ take the distance y from its neutral axis, that is neutral axis length of the section from its neutral axis, neutral layer. Clear? And then shown here the diagram after bending. So here before and after. So the radius of curvature is R. So the theta is the angle subtended at the center of the arc, and the arc of circle with O as a center. And I already considered here layer PQ at a distance y from RS, and then the written equation, the delta L, the decrease in length of the layer PQ minus P dash Q dash, and you have calculated strain and delta L by original length, the change in length by original length. So according to the diagram, I have derived P dash Q dash by R dash S dash is equal to R minus Y by R. So here simplified this equation, and finally we got strain is equal to Y by R. So original, that is the original length is Y, change in length is Y, and then the original length is R. So that the PQ and is equal to R dash S dash is neutral axis, and then according to the assumptions have taken, the stress is directly proportional to strain. It follows Hooke's law. So that's why the strain of a layer is proportional to its distance from the neutral axis. So the bending stress I have calculated here. So from Hooke's law, here taken stress is equal to bending stress is directly proportional to strain. Now taken elasticity, and the written equation are like this: sigma b is equal to y by r into E. So you can write y into E by r, and then the G and R are constants in this expression. Therefore, the stress at any point is directly proportional to y. So that is the distance of the point from the neutral axis have taken. So the equation may be also written as sigma b by y is equal to E by r. So here you can take, suppose you are considering section the modulus of say moment of inertia, that is I. So you can take I value, so moment of inertia, and also you can take section modulus or modulus subsection. So that is for circular beams, per circular pi d to the power of 4 by 32. So this is for circular one pi d to the power of 4 by 64. So you suppose if you are considering this moment of inertia and section modulus, you can write this equation sigma b by y is equal to E by R is equal to M by I. Clear? So you can write I by section modulus is I by y. Z is equal to, you may write I by y. So the equation you can write, suppose a bending stress, take this 2, sigma by y is equal to M by I. You can write bending moment is equal to sigma b into I by y. So again, you can take, you can write, so this equation sigma m is equal to sigma b into I by y is, in place of I by y, you can write section modulus. So that the bending moment, bending stress is m by z. Bending moment, the bending stress is equal to bending moment upon section modulus. So we are considering, you are taking the section modulus, you can write the bending stress equation like this, sigma b is equal to m by z, or m is equal to sigma b into z. If you know the bending stress or section, you can calculate the bending moment. Clear? So similarly, take this 2, E by R is equal to M by I. So any value, any 2 you can take, and according to the given problem, you have to take this, you have to write the equation. So that this is sigma by y is equal to E by R is equal to M by I. This is bending stress equation. Bending stress equation. Clear? So the y is the distance of the point from the neutral axis taken. So in a beam, after bending, the neutral axis, this one, neutral axis. So you take a small elemental section. So for 2D, so like this, this is neutral axis. You have to take this y like this. Clear? So for circular section, cross section, so this circular cross section, so you have to take y like this. So this the bending stress equation, the bending moment, and then this modulus moment of inertia depends upon the section of the given beam. Clear? But the basic equation, the bending stress equation, have to write sigma by b by y is equal to E by R. Take this E is the elastic constant, R is the constant for radius. There is no change. These two are constant. You may write this equation like this. How to solve the problems according to this equation. So already you know this. This is E is sigma b bending stress and Young's modulus, and y is the distance of section from neutral axis, and radius of curvature already we have seen. So finally, the important note is the bending stress is inversely proportional to the radius, and therefore the maximum stress is radius should be minimum. The maximum stress, the radius should be minimum, and the minimum stress at the radius should be maximum, vice versa. So these are the references I have taken for this PPT. Ramamrutam, the strength of materials, the publishers are Ganpati Rai, and then R.K. Rajput, strength of materials. Title of the book is Strength of Material, and R.K. Bansal, title of the book is Textbook of Strength of Materials, and R.S. Kurmi and Gupta, the title of the book is Strength of Material. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.